Signals and systems, system classification, series on signals and systems, lecture number 1.18. System is a physical structure. It may have several other subsystems. Each subsystem may consist of several components. Hence, at the basic level, it is component, and at the overall level, it is system. A system can be viewed as an interconnection of several components. Of course, any arbitrary interconnection cannot be a system. There is a fundamental condition for the interconnection to be called a system. A system is a system only when it is capable of doing or capable of serving a purpose. Utility is an important aspect for a physical structure to be called as a system. Systems and signals, these are related. If signals are software, systems can be considered as hardware. Together, systems and signals, they serve us. They serve a purpose. They do certain work to the mankind. In the present session, the focus is on classification of systems. Several different classifications are available. Those classifications are mentioned and explained. Before going to the classification, a brief description of system along with its definition is given. Now, let us move further and start the session with a definition for a system. System is an entity. It is a physical structure. This physical structure is there to accomplish a task, to serve a purpose. How it serves the purpose? It manipulates one or more signals to serve the purpose. In this process, yields new signal or new signals. Here, in this definition, important aspect to be kept in mind is system is a physical structure. It is there to accomplish a task. While it is functioning, while it is put to use, during its use functioning, it manipulates one or more signals and gives out a new signal. In case of multi-output systems, more than one signal comes out of the system. Now we move on to various classifications of the systems. First, we consider a classification where systems are divided into linear and non-linear systems. What is linear system? What is non-linear system? What is the difference between the two? A system is said to be linear if it satisfies the principle of superposition. That is, the response of the system to a weighted sum of several signals must be equal to the same weighted sum of output signals, each output signal being associated with particular input signal acting on the system independent of all other signals. This is an exact definition of a linear system. In simplest possible terms, linear system is one which obeys superposition principle. To move further, for a linear system, the forced response as well as the natural response both has the additivity and homogeneity property. Both these aspects, additivity property, homogeneity property, these two, they are possessed by linear systems. Some more points regarding linear systems. The characteristics of a linear system, they are independent of initial conditions and applied inputs. The system behavior doesn't change with the inputs, doesn't change with the initial conditions. Linear systems can be classified into time invariant systems and time variant systems. A system that violates the principle of superposition is said to be nonlinear. If superposition is obeyed, then it is linear, otherwise it is nonlinear. For a linear system, the total response can always be decomposed as forced and natural responses. For nonlinear systems, the total response is very different from their sum. Here, he is differentiating linear systems from nonlinear systems. A system is said to be time invariant if a time delay or advance of the input signal leads to an identical time shift in the output signal. Linear time invariant system is being described here. It says a time delay or advance of the input signal leads to an identical time shift in the output signal. For time invariant systems, the forced response as well as natural response both have the time shifting property. Stated in other way, characteristics of time invariant systems do not change with time. These systems are characterized by linear equations with the constant quotients in general. Example, this is a equation, a linear equation. See, quotient, here is A, here is B, these are all constants. The constants in their characterizing equations indicate that the systems are linear. Some more points on linear time invariant and linear time variant systems. The most important implication of linearity and time invariance is characteristics of such a system can be completely determined from any one input-output pair. As already mentioned, properties of linear systems are independent of input. In other words, it behaves in the same way. Its behavior is same on any input. A consequence of that particular aspect here is being mentioned. In time variant systems, a time delay or time advance of the input signal, it does not lead to an identical time shift in the output signal. An example for time variant systems is linear modulator. The characteristics of time variant systems change with time. These systems are characterized by linear equations with time-dependent quotients. Example is d square r by dt square plus dr by dt plus 2t plus 1 r equal to ft. This is forcing function, of course. Notice here one quotient is 2t plus 1. Time is there in this quotient. The quotient is time dependent 1. Therefore, as it is not a constant, it cannot be linear time invariant system. It is time variant system. Another classification is into causal and non-causal systems. A system is said to be causal or non-anticipatory if the current or present value of the output signal depends only on the present and or past values of the input signal, but not on the future input. The causality of an LTI system, LTI here stands for linear time invariant. The causality of an LTI system is equivalent to its impulse response being a causal signal. If the impulse response of the system is causal, then the system is causal system, non-anticipatory system. Its output depends only on the present and or past inputs. If the output signal depends upon the future values of the input signal too, then the system is called non-causal. Another classification is into dynamic and static systems. A system is said to possess memory or dynamic system if its present output depends upon the past or future values of the input signal. The system is called memoryless or static if its output depends only on the present value of the input signal, but not on the past or future values of the. Notice the difference between causal and non-causal, dynamic and static. A memoryless system is linear if and only if its input and output can be related by a straight line passing through the horizon. Another classification is into invertible and non-invertible systems. A system is said to be invertible if the input of the system can be recovered from the system output. The unit impulse responses of invertible system and inverse system when convolved give a unit impulse. This is an important aspect to be kept in mind. An example for invertible system is communication system, transmitter, receiver. Input is given to the transmitter. Output of the receiver is signal which is input to the transmitter. Therefore, a communication transceiver is an example for an invertible system. Another classification is into stable and unstable systems. Stability of a system is defined in several ways. One concept is BIBO stability. A system is said to be bounded input, bounded output, that is BIBO stable if and only if every bounded input results in a bounded output. The output of such a system does not diverge unless input. If the system gives bounded output for bounded input, then one can say, for all practical purpose, the system is stable. Otherwise, it is unstable. Another classification is into lumped and distributed systems. A system consisting of lumped or discrete elements like resistors, capacitors, and inductors is called lumped system. As already mentioned, within a system there may be small systems called subsystems, and each subsystem may be made with several components or elements. These elements may be lumped or discrete, or they may be distributed. A system consisting of lumped or discrete elements like resistors, capacitors, inductors, that system is called lumped system. In these systems, the energy of the system is considered to be stored or dissipated in the discrete elements, and the disturbance initiated at any point in the system propagates instantaneously to all the points in the system. But in practice, in reality, it is not so. Everything takes time to move from one point to another point. Even light also. Light also cannot move instantaneously from one point to another point. It moves with certain velocity equal to c, maximum velocity. But in the analysis of lumped element systems or lumped systems, normally in the initial stages, we assume that everything travels with infinite speed for the sake of simplicity of analysis. Of course, later we consider the finite velocity of the disturbance moment to move further. Description of these systems requires ordinary differential equations with independent variable t time. Some more points regarding lumped and distributed systems. Distributed systems are systems like transmission lines, waveguides, antennas, which are not possible to describe by lumped elements. If we see at transmission lines, we can find them everywhere, one pole to another pole. It may be, let us say, 100 meters. The transmission line spreads. It is there, existing from one pole to another, and that pole to the next pole. So it is there. It is distributed. It is existing everywhere. Wherever it is, it is. So it is not possible to describe them with lumped elements. In these systems, it takes a finite amount of time for a disturbance to propagate from one point to another. Here we have to take the finite velocity of the disturbance. It is a must. Description of these systems requires partial differential equations with independent variables t, time, and x space. In a lumped system, the effect of past input on future output can be summarized in a finite number of initial conditions, whereas the distributed systems require infinite number of initial conditions. So in this para, he is explaining a salient feature, a difference in the functioning of lumped and distributed systems. Another classification is into CT and DT systems. Here CT stands for continuous time, DT stands for discrete time. A system is called continuous time system, CT system, if it accepts CT signals as input and generates CT signals as output. A system is called discrete time or DT system if it accepts DT signals as its input and generates DT signals as output. So briefly, CT system is one which accepts and which gives out DT signals. A DT system is one which accepts and which gives out DT signals. Another classification is into analog and digital systems. A system is called analog system if its input and output are analog signals, and a digital system if its input and output are digital signals. Now, so far, focus is on classification of systems. Now we move to another area, a small topic. This is about physical realizability. What is physical realizability? One can plan, one can design so many things on paper. One can visualize, one can imagine several exotic things in the mind, but they need not be physically realizable. Only some can be realized in practice. Some cannot be realized, cannot be produced, cannot be created or generated in reality. Physical realizability. Under this topic, we consider one or two aspects which give us an indication whether a particular idea, a particular plan, a particular imagination, visualization is physically possible or not. Basically, there are two conditions which speaks, which tells, which gives some indication to us whether a particular idea is, a particular visualization is realizable or not. One such condition is causality condition. It gives us some information regarding whether your idea is practicable or not, realizable or not. Let us see what it says. The unit impulse response, h of t, of the system must be causal for its physical realizability. You have a system on paper. To know whether it is physically realizable or not, what you need to do is first compute impulse response of the system and then test whether it is causal or not. If it is causal, then there is possibility for physical realization, otherwise not. So h of t is 0 for t less than 0. This is a time domain specification for physical realizability. Another criteria is also there. It is called Paley-Wiener Criterion. For a system to be physically realizable, the magnitude function h of omega has to satisfy two conditions. First one is it must be square integrable. Integral minus infinity to plus infinity h omega whole square d omega, it must be less than 0. Square integrable. And then it must satisfy the integral given here. Minus infinity to plus infinity, natural logarithm h of omega divided by 1 plus omega square d omega. It must be less than infinity, which is a necessary and sufficient condition for the physical realizability. Of course, this is known as Paley-Wiener Criterion. One or two observations regarding Paley-Wiener Criterion. It can be noticed for physical realizability, the magnitude function h of omega must be 0 for some discrete frequencies, but it cannot be 0 over a finite band of frequency. The amplitude function cannot fall off to 0 faster than a function of exponential order. These are two aspects which are built in Paley-Wiener criteria. So before going to conclude, let us recollect various aspects that are considered, discussed, explained in the present session. To begin with, a formal definition of a system is given, along with a brief description, explanation of the definition. And then we moved into various different classifications of the systems. After exhausting classifications, a small brief on physical realizability is given, and then two tools. One is a time domain tool, another is frequency domain tool. Two tools which are useful for us to test whether our idea, the system that is in our mind, the system that is there on the paper, is physically realizable or practicable or not. Those aspects are also considered. Hope this session is useful to you. We meet again in another session with a new topic very soon.